divide this by 2, right? So this becomes the chi-square divided by its own degrees of freedom, right? And then what you do is take this quantity, yeah, this is the unrestricted one. Take the unrestricted one, right? So you divide this by 1 upon sigma square 1 upon n minus 3 summation E hat I unrestricted square. Right? So what you have here is again a chi-square below n minus 3 divided by its own degrees of freedom, n minus 3. And then you will cut off sigma square, sigma square. So the unknown quantity you put in the numerator and the denominator, you get rid of. So what you get is you get an F, because the numerator is a chi-square divided by its own degrees of freedom. The denominator is a chi-square divided by its own degrees of freedom. So basically what do you have? Summation E hat I r square minus summation E hat I u r square upon 2 in the numerator, right? Upon 2 in the numerator, divided by summation E hat I u r unrestricted by n minus 3 in the numerator, denominator, right? In the denominator. Well, because what we are saying is, what is this anyways? The distance, the gap in the, if you look at, what is summation E hat I square? E hat I square is the residual sum of squares from the restricted mode. Summation E hat I u r square is the residual sum of squares from the unrestricted mode. So what we are really comparing numerator is the gap between them. The larger this gap, greater is the evidence against the null hypothesis. Because summation E hat I square is the sum of squared errors resulting from imposing a certain restriction. If the restriction is not supported by the data, then the summation E hat I square will be bigger than summation E hat I u r square. The errors, sum of squared errors from the restricted model will be bigger than the sum of squared errors from the unrestricted model if the restriction is not. If the restriction is true, they will be the same. Right, so the larger is this quantity, the greater is the evidence against the null. What we are saying here is, we are comparing this gap as a proportion of the sum of squared errors of the unrestricted range. So what we are saying is, how large is this gap? Now, the gap between the residual sum of squared errors from the restricted regression, the residual sum of squares from the unrestricted regression, how large is this gap related to the residual sum of squares from the unrestricted regression? Right? So that's a kind of it's a kind of a percentage, right? Okay, it's a kind of a percentage, right? It can also be negative, and this follows the F distribution. The denominator part is the sum of squared errors from the unrestricted regression divided by F. In the previous one, see, under the null hypothesis, there was a sigma square here, but I do not know sigma square, so I can't actually calculate it. So what I did was, under the null hypothesis, in the numerator, if you put the summation E hat I square, basically, upon sigma square into 1 upon n minus 3, there is a chi-square divided by its own degrees of freedom. The moment I do that, I can take this sigma square out and this sigma square out, and the unknown sigma square out goes away from the numerator and the denominator. I am left with this quantity. I can calculate, and the known distribution I can compare. Right? Yeah.
So then the distribution will have to be numerator and n minus 3 denominator.
Exactly. The F distributed 2 degrees of freedom in the numerator, n minus 3 degrees of freedom in the denominator. Suppose I was testing k restrictions, not 2. Then what will be the numerator degrees of freedom? K. So the numerator degrees of freedom is exactly equal to the number of restrictions I have and the Denominator degrees of freedom are the number of parameters being estimated in the unrestricted regression. The number of parameters being estimated in the unrestricted regression is the degrees of freedom in the denominator. In the numerator, the degrees of freedom are the number of restrictions that you will impose. So now tell me how you will test this. ये हेटेरोस्केडास्टिसिटी टेस्टिंग के लिए किया ना सब कुछ, तो कैसा करेंगे? He says F test. कैसा करेंगे लेकिन? अगर नल हाइपोथेसिस क्या है? All the A's at A at A1 and A2 are equal to 0. So do you see an exact parallel between what I am doing there? It's the very same thing, no? So you have a restricted regression and unrestricted regression and so on and so on. But the whole problem is here that the error terms might not necessarily be normally distributed. So if the error terms are not normally distributed, what do I do? Then I can use this. If the error terms are not normally, I'm not sure the error terms are normally distributed, not normally distributed, then I can use this. So what do I do? Then there is a man called Engel, right? Okay? This man got a Nobel Prize in economics for doing many things in econometrics. Robert Engel. Okay? Fine, please look up Robert Engel and also look up Clive Granger on the screen. Right? So Robert Engel and Granger both got the Nobel Prize in econometrics in the same year. Right? So you have to find out which year and all that. What Engel said was, Engel actually, if you will come to the third semester and take up a paper called Mathematical Foundations of Statistics, of Economics, Statistical Foundations of Economics rather, in that paper you learn how to generalize this test to cases where the error terms are not normally distributed. Okay, there is a test called Lagrange multiplier test. Okay, the same Lagrange multiplier for mathematics, we will use it in statistics as well. There is a test called the Lagrange multiplier test in, so basically best test in statistics. You see why would Lagrange multiplier come into the picture? There is a constraint, no? We are restricting, so what we are doing is, we are putting a constraint and minimizing the sum of squares in the unrestricted regression. If the constraint is binding, then lambda must be positive. If the constraint is not binding, lambda must be equal to 0. So if you calculate the lambda there and then you take tests on that lambda, you should be able to get a hypothesis test which does not depend upon the distribution of the error. Right? And how do you test for lambda? It's very simple. You simply do this regression. Okay? And then you calculate the R square of this regression. We have not talked about the R square of a regression, have we? No. So I'll quickly tell you what's the R square of a regression. Okay? So think of, and that's something which is important, the R square of the regression is the following. So if I have think of alpha plus y is equal to alpha plus beta xi plus ei. Okay? If I y is equal to alpha plus beta xi, or can I simply do away with all this here so that maybe I can write it right. Right? So if I have y is equal to alpha plus beta xi plus ei. Okay? Now, think of yi minus y bar. The value of y minus the mean value. This can be written as if I add and subtract the same quantity, doesn't matter, make a difference, right? Now think of squaring this. Okay? And then summing over all the i's. Okay. Right? So I have yi minus y hat I plus y hat I minus y bar. Okay? Let me think of this as A. Let me think of this as B. So what do I have? A plus B the whole square, which is equal to what? A square plus 2ab plus b square. Right? Everybody is saying this. Right? So this is now equal to summation yi minus y hat I square plus y hat I minus y bar square plus 2 summation yi minus y hat I, right, y bar. Sure? Now consider this term. Let's consider that term carefully. Realize that this is nothing but e hat I, yi minus y hat I. Okay, and I'm going to at the moment look at 2. Let me keep 2 out of the bracket. I have to look at the term inside. So this term becomes summation e hat I, right? Y hat I minus y bar. Yeah, this is equal to summation e hat I y bar, y hat I minus y bar summation e hat I. Y bar is a constant, no? So I can take it out of the summation e. What is summation e hat I? What is summation e hat I? 0. Yeah? Summation e hat, because those two equations come, na? Summation xi, ei is equal to 0, summation ei is equal to 0. Right, so because this. Right. This is equal to yeah? Right? This is equal to we now see that everything will be 0 because summation e hat I is 0, this first part will be 0. Yeah? And summation xi ei is equal to 0, so the second part will be 0. Right? Sure? So that means that this side is equal, this square is equal to this square plus this square. Right? Okay? Now what is this? This is the total distance of y from y bar. Total distance of y from its mean is this, summation yi minus y bar square. We are saying that this sum can be broken into 1 is equal to summation e hat I square plus summation y hat minus y bar square, right? So, because y minus y hat I is e hat, summation e hat I square. So what is y hat I minus y bar? It's how much my y hat is above y bar. So it's the difference in each conditional mean of y from its average. It gives you the conditional mean of y from the average of y. Right? Okay? So we are splitting the distance from the gap between y and y bar into one part which is due to the regression y I hat minus y bar, the gap between y I hat and y bar, which is happening because the y hat I had taken a particular value coming from the regression, and there is a part which is not explained by the regression. So the total variation in y, or the total sum of squares in y, can be written as explained sum of squares plus the residual sum of squares. Right? So PSS can be written as RSS plus PSS. Now if I divide throughout by PSS, what will I get? PSS upon PSS is RSS upon PSS plus PSS upon PSS. Right? Or you will get, now where do I write this? Or you will get yeah? Sure? Now what is ESS upon TSS? Sorry, 1 minus RSS. Yeah. What is RSS? What is ESS upon TSS? What is TSS? The total variation in y. What is ESS? That part of that variation is explained by the regression model. So ESS upon TSS is that part of the variation in y which is explained by the regression model, which is equal to 1 minus RSS by PSS. This quantity is called the R square of the regression. Okay, this quantity is called the R square of the regression. What is the highest value that this can take? 1. Why? Because it explains everything. So all the RSS are 0. So ESS upon TSS will be equal to 1. All the variations explained. What is the lowest value that it can take? 0. Because it says that nothing is explained by the model. So ESS upon TSS is 0. Right? Okay, this is a quantity called R square which will lie between 0 and 1. Closer it is to 1, the better. Right? Now what Engel proved was that if you do this regression, okay, what Engel proved was, Robert Engel proved was that if you do this regression, take the R square of this regression. Okay? Take the R square from this regression. Multiply that by the number of observations that are there in the regression. Say T. Do this regression. Take the R square of this regression. Multiply by the total number of observations. Under the null hypothesis, this will follow the chi-square distribution. In this case, with 3 degrees of freedom. Or in general, if you have P restrictions, P degrees of freedom, whatever the distribution of the error. So what Engel said was, most of this problem, we can't do the error test with the error but not be normally distributed. Engel actually proved that if you take the regression curve, if you do this regression, if you test the null alpha 1 is alpha 2, alpha 3, alpha 1, alpha 2, alpha 3 is equal to 0, right? Alpha 1, alpha 2 is equal to alpha 3 is equal to 0, then what you must do is you must do the regression, the upper regression, that is you must do the unrestricted regression, calculate the R square of the unrestricted regression, multiply by the degrees, number of observations that you have, P, right? Okay, P actually you should do it with the correct thing would be do it with the degrees of freedom, right? Multiply by the degrees of freedom. Right, so degree of freedom will be T minus 3. T was the number of available observations. So make it clear, multiply by the degrees of freedom. And then the resultant will be chi-square distribution under the null hypothesis, irrespective of what is the distribution of the error. But that's an asymptotic result. You need a fairly large sample size for that. Right? So with a fairly large sample size, you can use this is called Engel's LM test. It is also called the BPG test, Broish-Pagan-Godfrey test, right? Broish Pagan and Godfrey test. Right? Royce, Pagan and Godfrey test. Which spelling you can find in the text? Royce, Pagan and Godfrey test. So df into r square is the Royce, Pagan and Godfrey test. Well, while we are at it, let me also tell you that the r square is a good measure, but it has certain limitations. Yeah.
So why is the chi-square 3 degrees of freedom?
Because there are 3 restrictions. If there are p restrictions, we have p degrees of freedom. If there are 6 restrictions, we have 6 degrees of freedom. If there are 20 restrictions, we have 20 degrees of freedom. Everybody gets this? Okay, while we are at it, let me tell you a few things about the r square. The r square is very often measured as a goodness of fit. It is used to measure how good your model is fitting. Right? That is, higher the r square, the better. There are 2 provisos that. One is, if the model is misspecified, you cannot do. In this, if x and e are uncorrelated, no matter how high your r square is, you can't say it's a good model. Why? Because the r square is derived on the assumption that summation xi e hat I is equal to 0. We use the assumption that summation xi e I is equal to 0. And if xi e I is actually not equal to 0, this is not the formula for r square. Right? So if your model is misspecified, if there are measurement errors in x, etc., then whatever high your r square is, it's not going to make any difference. It's going to be a trashy model, continue to be a trashy model. Right? So, because unfortunately many times r square is a single measure of goodness of fit. How good a model is depends upon what its r square is. That's not the right way to look at a model. Right? Okay? Sure? Second thing is, you can compare r squares for models which have only the same dependent variable. The y has to be the same. You can't compare across models where the y's are different. You can't compare across models where y's are different, right? Okay, y's are different. Sure? Is it clear? Okay. The third point about r square is a really damaging thing. Okay, which has nothing to do with the Engel's LM test. There is a standalone problem with the r square, which happens as it is. Now suppose I have a model which has a certain r square. So y depends upon, say, some x. And I add another variable to the regression model. So y depends upon x and z. Y depends upon x and z. Now just because I have introduced another model, x, another variable z, now the variable z might not be relevant for y. But there can be some chance relationship between one particular value of z and one particular value of y. Which means that my sum of squared errors will fall a little bit. If my sum of squared errors falls a little bit, my RSS will fall a little bit. So my r square might actually increase when I add an additional. Unfortunately, but that's not right, because what should happen is, when I put an additional variable in the regression model, I reduce my degrees of freedom, because I'm putting an additional restriction for that coefficient. So if my degrees of freedom go down, I must also penalize my model. Putting the variable will improve the fitness or goodness of the fit of the model, but make it a better model. Right? It will reduce this RSS, but it also reduces the degrees of freedom. Right? So there is a cost that I am paying, because if I reduce the degree of freedom, the variance of the error term will increase and all those kinds of things will happen. There is a cost also to the model by increasing and putting in an additional variable in the regression model. Is everybody getting this? The simple R square measure is an asymmetric measure, because it gives you the benefits of putting in an additional regression, additional regressor, an additional explanatory variable, but it does not penalize you for the cost of reducing the degrees of freedom. So what we often do is, to overcome this problem, we form something called an adjusted R square. Yeah? Which is one so I will write it here. Yeah, so I divide the numerator by n minus k, I divide the denominator by n minus 1. right? I divide the denominator by n minus 1. What is the advantage of doing this? Suppose I put in an additional explanatory variable in my model. What is the impact of that? Will k increase or decrease? K is the number of explanatory variables in the regression model. K is the number of explanatory variables in the regression model. So if I put that additional explanatory variable, k will increase. If k increases, what happens to this fraction? The fraction decreases. Right? If k increases, this fraction decreases. The numerator of this fraction decreases. So what happens to the whole fraction? Sorry, look here. If k increases, then this falls, right? If k increases, this falls. If this falls, what happens to this? Increases. So the whole fraction increases. So what happens to the adjusted r square? It falls. So the cost to putting in an additional variable. But it can also rise. When will it rise? When that additional variable reduces my residual sum of squares. So that additional variable, if I include an additional variable, it will have two impacts. One is, it will of course reduce the degrees of freedom, so n minus k will actually become smaller, but it might actually also improve the fit of the regression, reduce the errors in the regression, so RSS will also fall. So whether adjusted r square increases or decreases depends on which of the two effects counterbalances another. If the cost of putting an additional variable, the reduction in the degrees of freedom outweighs the benefits of putting that variable, adjusted r square will fall. If, on the other hand, the benefit of an additional variable improves the goodness of a fit so much that it outweighs the cost of the reduction in the degrees of freedom, the adjusted r square will go up. Right, so very often generally it's better to use the adjusted r square rather than we call it the r bar square. The adjusted r square is the r bar square instead of the r square if you are comparing between models, right? Because they might have different number of explanatory variables. All that requires the y to be the same and x's could be different. So you obviously need to account for the fact that one model has a fewer degrees of freedom than another, and that's what the adjusted r square does. But Engel's LM test essentially takes this, right? Engel's LM test essentially uses r square into the degrees of freedom. And if you do a time series course later on, you realize that this is actually used to model risks in stock markets and all those kind of things. Because the risk is really the variance. So if you think of the returns as some term E, right? And if the variance of the returns is varying in time, you are essentially testing for heteroscedasticity of the returns, right? If the returns become more volatile, then you're testing for change in variance, right? So you're doing some kind of a test, and this will be very important to you in testing for what are called arch and large models, which are very important in modeling, risk modeling in the financial world. If you take the time series courses, you will do this.